So what I want to do is use the label mover feature to calculate the current flowing in the pickup coil as a function of frequency. So I'll illustrate this label mover feature. So under the Tools menu, I go to Parametric Analysis with Label Mover. Okay, and I'm in Serial Analysis. What I want to do is add values. And we want to look at the pickup coil with the total current flowing in the pickup coil. And actually we can expand this if we want to look at the imaginary parts, and also the phase. So I'll simply add this for the time being. Okay. Now we want to record the steps. So in recording the steps, we can change the model geometry, or we can change the physical properties of the model. So I want to change the problem properties, that is the frequency. Okay. Currently the frequency is 50 Hertz. So let's increase this 100% initially. We can add a step. Okay, now the frequency is 100 Hertz. I'll repeat the last step. So each step we're increasing the frequency 100%. It's 200 Hertz, 400 Hertz, 800, 1600, 3 kilohertz, 6K, and we'll go to 12K. So I've repeated the step 8 times. We'll close this. Now we get results. Okay, so initially the total current was 0.27. Now as we increase the frequency, the current in the coil, the pickup coil, is going to be increasing with frequency. And later on we can plot the results. We can plot the total current versus frequency. Also we can export the data if we want to import this into Excel or another spreadsheet. So QuickField is creating a new model file for each run here, and it's saving this in a separate folder. Which we can see down here. So all the new model files will be saved in this separate folder. So if you didn't like your particular run, you could delete the folder and go back to your original model file. Can we bring this back up? Okay, we have 2 more iterations of the model. Okay. Now it's finished solving all 8 simulations, and now we can plot the total current in the pickup coil as a function of frequency here. And we can import this into a spreadsheet. As well, we could have plotted other parameters too, besides the total pickup coil, for example, the real and imaginary parts, as well as the phase. The next simulation I want to look at is using a ferrite in the eddy current simulation, where we use the ferrite to focus the eddy current into the object under inspection. So I'll put up all this. So this is the model file. Once again, we have axisymmetry. Now, in addition to the circular excitation coil, I've surrounded it with a high permeability mu metal cup core. So this, if I look at my block labels, this is the air region, the aluminum plate as usual. This is the coil, where we have a copper coil carrying, actually in this simulation I've given it a 1 volt potential. So we have a choice of assigning a voltage or current to our coil. And the mu metal has a permeability of 10 to the power 4. So this would be about the highest permeability material that you could obtain, used for magnetic shielding and so forth. The mesh is kind of fine in this region. Doesn't necessarily have to be this fine. If we want to see how many nodes we have altogether, we can look at the properties. We have roughly 7,500 nodes. The solution is up to date. However, I'll solve it again so we can get an estimation of the solution time. Now, in this simulation, you can see that the magnetic field is screened in the external regions here. However, the flux density is increased beneath the ferrite, and we can plot the eddy current density and compare with and without the ferrite. I will go ahead and turn off the field lines. Zoom into the problem. I will create a contour beneath the surface here. Okay, I'm creating the contour by hand. You can do this with keyboard. XY plot. And this gives us a profile of the current density. This is actually the same as the eddy current density. There's no source current in this region. And the effect of the ferrite is to make this a more narrow peak. So more of our eddy current is going to be condensed underneath the probe, as well as shielding the eddy current from external regions. So I want to look at the problem now with the lap joint, the rivet, and we can solve that. It's essentially a single filamentary coil above a lap joint, and I'll zoom in here so we can see the geometry. This is the air region. Now, as I've labeled this, the pitted corrosion is labeled as an air region in the second layer here. The aluminum plates, and this is the rivet here, and this is the head of the rivet. The boundaries of the edge of the solution region are given 0 vector potential. This is the coil, a single filamentary coil with 1 ampere current, and the problem properties. AC magnetics. Notice we can also look at this in transient magnetics. If I want to have a pulsed eddy current simulation, which I'll be showing in a little bit. Okay, so I'll increase the frequency a little bit. Okay, so you can see the eddy current density. There's no eddy current that's flowing in the corrosion pit since it has zero conductivity, the same as air. Now I could sweep the frequency of the excitation coil like we did before and monitor the change in magnetic field as a function of frequency or coil liftoff or coil geometry, and design a coil that is best suited for detecting these types of defects. So let's go ahead on and look at the defect-free eddy current field here. If I go back to my geometry file, what I will do is simply switch this back to aluminum. Okay, and then we can resolve the problem. And you can see that the eddy current is now flowing in this region. If I want to look at individual values, I can use this tool. If I just want to look at the eddy current density and other parameters within the model, I can find local values using this tool.